In this video we'll derive a method of finding the x coordinates of all of the conjugate points. So if we start off looking at the solution to the Jacobi accessory equation as a second order differential equation, and the general solutions of that type of equation can be written in this form: u of x equals b1 u1 of x plus b2 u2 of x. Now we know we've devised it so that u of x equals 0 at some point A, and the u of x will also equal 0 at the conjugate points. So we can write then that 0 equals b1 u of A plus b2 u of A. So if we rearrange that, then that can be written as minus b2 upon b1 equals u1 of A upon u2 of A. Now that's just for one particular conjugate point, so it's the same for every conjugate point. So we can then add in the factor that this here is going to equal u1 of x upon u2 of x. Okay, so that means we can use this little section here in order to find the x coordinates of the conjugate points, because we know from the previous videos that partial y upon partial c1 is equal to u1 of x. So that's us differentiating the solution to the Euler-Lagrange in order to give us a part of the solution to the Jacobi accessory equation. Now the other part, partial y upon partial c2, is equal to the u2 part of the solution to the accessory equation. So it means that we can substitute these into this little section here. So you're going to end up with partial y upon partial c1 divided by partial y upon partial c2. Well, that's going to equal partial y upon partial c1 upon partial y partial c2 at the point x equals A. So we can use this here in order to provide a solution to, or find the x coordinates, which are called the abscissa of all the conjugate points. Now we're going to look at an example of that in one of the upcoming videos, and once we've completed that example we'll go through a case study of the catenary, and we'll look at everything we've done so far with regards using the catenary as an example. Okay, thank you very much for listening, and goodbye.